Okay, so first functional group we're going to talk about is alkanes. So you're going to find that when it comes to organic molecules, it's a really complex naming system, but everything works off of that same general set. So alkanes itself can be a little bit overwhelming because there are so many things to consider, but you'll find when we get into further functional groups, that it's actually not too bad because you're just working off that same set of rules with a couple of tweaks, okay? So how are you going to recognize an alkane? Because that's always the first thing we want to do when we're either naming or drawing is figure out what type of molecule we actually have so that we use the right set of rules, okay? So alkanes are what we call the simplest type of hydrocarbon, okay? Hydrocarbon because they're only made up of hydrogen and carbon. They also only have single bonds, okay? There's no double and no triples. If you have those, you're gonna have a different type of molecules. Okay, because they only have single bonds, this is why we consider them to be saturated hydrocarbons. Okay, you're gonna see when we get into the types of reactions, hydrocarbons that are saturated are gonna do different types of reactions than things that are unsaturated. And that's because these guys only have single bonds, and the ones that are unsaturated are going to have double and triple bonds, okay? So, other thing is, we consider these to be aliphatic. Okay, you're going to find that when it comes to organic molecules, they're all either considered to be aliphatic or aromatic. Okay, you're going to find when we get to molecules being aromatic, they contain a very specific structure in them. So basically, if it has that structure, it's aromatic. If it doesn't, it's aliphatic, which is why everything that we're talking about in this video is just going to be aliphatic. Okay, next thing you find with alkanes is they have a general formula of CnH2n plus 2. So what that means is if I have, let's say, 5 carbons, then N would equal 5. So that if I think about my H, if I had 2 times N, so 2 times 5, that would give me 10 plus 2. 10 plus 2 is 12. Okay, so where that general formula is more so helpful is that sometimes we're going to give you a formula like C5H12, and then we're going to ask you to draw it. Okay, and you being able to recognize that that's an alkane and that everything is a single bond is going to be important, because otherwise you're going to sit there and going to be like, I have no clue what I'm drawing. Should I have a double bond? Should I have a triple bond? So by recognizing that general formula, that's going to help you figure out what you have, okay? Okay, so when it comes to naming alkanes, my slide is kind of half off the screen. That's helpful. Oh, too much. Hold on, let me see if I can fix this. I don't know why it's doing that. That's really not helpful. Okay, so we have 3 general parts to any name that we are looking at. Okay, we're going to have a root, a prefix, and a suffix. Okay, they always go in that order. Okay, so we're always going to start with that root, or not the root. What am I talking about? Those are not in the right order. Sorry, it's going to go prefix, then it's going to go root, and then it's going to go suffix. Okay, what you find is each part of that name tells you something different. So the root is always going to be in a name. There's never not going to be a root in a name. Hold on, I'm trying to click on something and I can't click on it. Okay, so we're always going to have a root. Okay, that root is telling us how many carbons are in that main chain that we have. So if you think about yesterday, or not yesterday, I guess it's all today, everything's blurring together, or maybe it was yesterday, depending on when you watched it. We kind of had this structure happening here. I'm not drawing the hydrogens, but they're all there, right? So we have 3 hydrogens here, we had 2 here, 1 here, 3 here, and 3 here. Okay, but what you find is when we're naming, I don't want to say we don't care about the hydrogens, but we don't really care about the hydrogens. They're all implied to be there, okay? So when I'm looking at this, I want to start by figuring out what's my longest chain of carbons. So sometimes it goes straight across the page, right? So if I look, here's 1, 2, 3, 4. I definitely could go across the page. But are there other ways that I could make a chain that's longer? So 1, 2, 3, 4, well, that's still 4. So it doesn't really matter which one I choose. But if, let's say, there was another carbon down here and then I went 1, 2, 3, 4, 5, then I would be choosing that as my longest chain. But right now, we can choose this as our longest chain, okay? So when I look at that, it has 1, 2, 3, 4 carbons in it. So based off the fact that there's 4 carbons in it, if we look down here, here's 4 carbons. The name for 4 is bute, okay? So here you have a little table. You have to know 1 through 10. So basically, based off of how many carbons are in that main chain, you choose the appropriate name. So if there was 1 carbon, we use meth, right? So think of methane, right, which is a common compound. That's telling us it has 1 carbon. 2 is eth, right, so ethane. And 3 is prop. 4 is bute. Usually you guys all giggle in class notes. You're like, no, Miss Chip, it's but it is bute, right? So butane, right? If you think about like what's in lighter fluid, it's butane. 5 is pent. 6 is hex, right? So once you hit 5, they become the names you're used to. It's just 1 through 4 that are different than the whole like mono, di, tri that you guys are used to, okay? So for now, you can kind of use the table to help you figure out what that appropriate root name is based off of the number of carbons you have. Ideally, you're reaching the point where you know what they are and you don't need to look at this anymore. So that's how you get your root. It tells you how many carbons are in the main chain. Okay, your suffix is also pretty straightforward. So the suffix part of your name basically tells you what family something belongs to. Right, so if you think about some molecules you're familiar with, right, you know of methane, you probably also know of methanol, right? So they both have meth in them, which tells me 1 carbon. But that ending of ane or that ending of anol tells me what other type of thing they have. So when we are dealing with alkanes, which have all single bonds, they all end with ane, okay? So when you see all single bonds and nothing else fancy happening, we are going to use ane as our suffix, right? So methane is telling me I have 1 carbon where everything that's attached to it is a single bond. If I have ethane, that's telling me I have 2 carbons where everything attached is a single bond. So if we go back to this molecule that we drew up here, we now know that it is a butane, right? And we know that because the bute is coming from the 4 carbons. And the ane is because everything inside of it is a single bond, okay? So the complicated part is this guy right here, okay, this side chain. Okay, we call it a side chain because when we figured out what our longest chain was, it wasn't part of it, okay? It's kind of hanging out of this boxed in area that we have. So where the side chain goes in the name is in our prefix, okay? Your prefix is going to tell you if you have any side chains. So some molecules will not have a prefix. And if they don't have a prefix, because they don't have a side chain. If they have a prefix, it's because they have a side chain. So how that prefix is going to work is it's going to tell you 2 things. It's going to tell you how big the side chain is, so how many carbons are in it. Like, does it have 1, like this guy does, or does it have 2? Does it have 3? The other thing it needs to tell you is where it is, right? Because if you think about this, I have 1, 2, 3, 4 carbons in my main chain. I need to know which one it's attached to, okay? So, general rule, it's never attached to the first or last one. If it's attached to the first or last one, it's actually part of the main chain and you just didn't recognize that that main chain took a bend, okay? So, how we indicate how big it is? Well, we use this same root name, okay? The only difference is what we end it with. So if I look at this, it only has 1 carbon. We look at our table, the name for 1 carbon is meth. So that means this is a meth. And then because it's a side chain, and we call them alkyl side chains, it's going to end with a YL. So it's a methyl, okay? So meth, because there was 1 carbon, which came from here, and ill, because it's a side chain, okay? So this is known as a methyl, okay? So now we're indicating how big it is. Now we need to indicate where it is. So how we indicate where it is, we're going to number the carbons in our chain. So numbering wise, we always have to start at one of the ends. So we need to look at both options. So if we number from the left side, this is carbon 1, this is carbon 2, this is carbon 3, and this is carbon 4. If we numbered from the other side, because that is an option, this is carbon 1, this is 2, this is 3, and this is 4. So how we decide which way to go, we want the smaller number, right? So this carbon is attached to this one. So either it's a 2 or a 3. The smaller number out of those two is a 2. So that means we're going to choose to number the blue way, not the red way. So my overall name for this, because it is attached to carbon number 2, so we're going to say that this is a 2-methyl. Okay, organic naming is a little weird in that we don't want to put a number next to a letter. So we're going to use a dash. Okay, so numbers are separated from letters using dashes. And you're going to find when we look at some other examples that numbers are separated from other numbers using commas. Okay, so now we need to put this whole name together. Okay, this prefix goes at the beginning, then we're going to have our root, then we're going to have our ending. So that means this guy is going to be called, I guess I'm going to have to use one of these. We are going to call it 2-methyl and then straight into the next name. Okay, no space. So 2-methyl straight into our root. So bute. Oh, fingers sticking to the mouse pad. Ane. They need a course in how to use your mouse pad to write a little nicer. But who knows, maybe by the end of this year I'll be a pro at this, okay? So that's how that's going to look. Okay, I'll do another video with a few other examples just because there are definitely a lot of, like, I don't want to say weird exceptions, but things that you do differently if you have multiple side chains, okay? But I know this is going to cap out in a couple minutes. Oh, look at that. A whole slide on steps on naming. This probably goes through all the different things that we were talking about, right? So identifying the root, identifying the suffix, right? So it's an ane, ends with ane. Identify your prefix, okay? So this does get into some of those weird exceptions that I was talking about, right? So start by figuring out how many carbon atoms are in each side chain. Then it starts getting into determine the alphabetical order for two side groups, okay? So I'm going to show you that in a separate video. What I'm going to do to finish this video out is just do those physical properties because it's pretty quick, okay? So physical property wise, we kind of talk about what it's soluble in and what its melting point and boiling points are like. So alkanes are all nonpolar molecules. If you think about last year, and I know for some of you it's been a while, we have no lone pairs on our central atoms, which are our carbons, and all the non-centrals are the same, right? All the non-centrals are hydrogen. So because of that, we find that these are nonpolar molecules. And if you also remember back to last year, we always talked about how like dissolves like. So that means alkanes, which are nonpolar, will not dissolve in water because water is polar, okay? So what will alkanes dissolve in? For the most part, what you're going to find that your alkanes dissolve in, well, it's not going where I want it to go, is these guys are soluble in hexane. Okay, so hexane is another alkane. The reason they're soluble in it is they have that same type of general pattern going on, okay? Melting point and boiling point, they only have London dispersion forces. So if we think about what that pattern is going to look like, we're going to find, well, that's not a very straight line, but you get the idea, that our alkanes, we're not going to do that, that's me clicking wrong, are going to look like this. Okay, the more carbons we have, the higher that melting point, boiling point is going to be because they have stronger London dispersion forces because they have more electrons.